Hello everyone, welcome to the series of lectures on nanomaterials. In this session, we are going to discuss about properties of nanomaterials, physical properties, chemical properties, optical properties, and electrical properties. I welcome you all to this session. Myself, Dr. Babu Batula, Professor and Dean, School of Sciences and Humanities, SR University, Warangal. In our previous sessions, we have discussed about nanoscale materials and what kind of materials we can call it nanomaterials, and we also discussed the importance of nanoscale. How can we distinguish macro materials, micro materials, and nanomaterials? And also we have discussed about the importance of nanomaterials or nanotechnology in various fields, in medical field, in electronics field, in materials field, in energy, and also in environmental applications. So we have discussed and also about the classification of nanomaterials. Okay, so we have discussed four types of nanomaterials: zero-dimensional materials, one-dimensional materials, two-dimensional materials, and three-dimensional materials. We have discussed in depth real real cases of the preparation of nanomaterials. Okay, in this session we are going to discuss about properties of nanomaterials. Okay, right. So before going to discuss about the properties, different properties, so I want to briefly explain the fundamentals related to the nanomaterials. Okay, so I want to briefly explain you about nanomaterials and also what are the reasons for this technology to have that beautiful properties. Okay, so you can, if you see this picture, you can understand the difference in size from macro size to micro size, then nano, then atomic scale. Okay, here you can see the object which is in macro scale. So what kind of objects can be considered in macro scale, what kind of objects are in micro scale and nanoscale and in atomic level. Here if you see here, a child, hand, finger, an insect. Okay, so all these comes under micro scale. Okay, micro scale. So micro scale is what can be seen with the naked eye. So whatever the objects we can see with our eyes, we can call them as macro scale objects. Okay, macro scale objects. Similarly, so by using microscope, if we are able to see some objects, then we can say that those are micro sized objects. Okay, here you can see hair and also cell, bacteria. So all this comes under micro scale. Okay, so we can able to see the hair, but if you want to see the individual hair or the clarity of the scalp, with respect to hair, so we need microscopes. Okay, so how can we define micro objects? Micro scale objects is too small to see with our naked eye. So usually we cannot see directly with our eyes in case of micro sized objects. Okay, so if we want to see micro sized objects, we need microscopes. Okay, we need microscopes. Similarly, see, here you can see the order in meters: 10 power 0, 10 power minus 1, 10 power minus 2, 10 power minus 3, right? So up to this we can say it is a macro sized. Okay, macro scale. So here you can see 10 power minus 4, 10 power minus 10 power minus 4, 10 power minus 5, 10 power minus 6, 10 power. Okay, so this range can be called as micro scale. Okay, micro scale. What happened to the camera? What happened to the camera? Just wait a minute. Okay, okay, let's start with this picture. So coming to the nano size, so nanofibers, virus, DNA. So these are all under nanoscale. These are all under nanoscale. Virus, DNA, these are all under nanoscale. So you can see 10 to the power minus 7, 10 to the power minus 8, 10 to the power minus 9. So usually 1 nanometer is equal to 10 to the power minus 9 meters, right? 10 to the power minus 9 meters. It is under nanoscale. So when you go to the atomic level, whenever we discuss about electrons, protons, neutrons, and all these things, it is in the order of 10 to the power minus 10 meters. So that we can say that it is a atomic level. Okay, atomic level, right? Atomic level, right? So if you see these some of the important points related to macro and macro to nano. So transitioning from macro scale to nano scale fundamentally alters material properties due to quantum effects and surface effects. So we have discussed very in detail in our previous classes that whenever a material transforms or changes from macro size to nano size, all most of the material properties will change, right? Most of the material properties will change. So for this change in material properties, there are two reasons. Okay, two reasons for this major change in the properties of nanomaterials. Okay, so what are those properties? Quantum effects and surface effects. Okay, then so at the nanoscale 1 to 100 nanometer, matter behaves differently as surface area dominates and quantum confinement takes effect. So how can we define nanomaterial as per our previous classes? So if any one of the dimension of any material falls under 100 nanometer, then we can say that it is a nanomaterial. Okay, we can say that it is a nanomaterial. So one of the dimensions must be less than 100 nanometers. Okay, less than 100 nanometers. So we have discussed this in our previous class, in classification of nanomaterials. So we have discussed zero dimensional materials, one dimensional materials, two dimensional materials, and three dimensional materials. So how is the quantum confinement in zero dimensional materials? In zero dimensional materials, all the three directions are restricted. Okay, all it is confined in along three axes. It is confined in three directions, three dimensions, or three axes. Okay, but if you take one dimensional material, it has confinement in two directions. It has confinement in two directions. But if you take a two dimensional material, it is confined in one dimension. It is confined in one dimension, and allows to stretch beyond nanoscale in two directions. But in case of three dimensional material, so there is no confinement. It can stretch in along three dimensions, but it must be under 100 nanometers. It must be under 100 nanometers. Okay, right. So classical physics, classical laws lose predictability and new phenomena emerge, such as discrete energy levels and enhanced surface activity. So as we discussed earlier, so we have majorly we have two types of mechanics: classical mechanics and quantum mechanics. Classical mechanics applied to macro-sized objects, right? Macro-sized objects. But at nano level, at atomic level, so more than classical mechanics, quantum mechanics plays a major role. Okay, quantum mechanics plays a major role. So because of the particle nature and wave nature, so quantum mechanics plays a major role at nano level. Okay, at nano level. So that's why we are saying here, classical laws lose predictability and new phenomena emerge, such as discrete energy levels. So as per classical, in case of bulk molecules, we have continuous energy levels. Okay, that's why it forms a band. That's why it forms a band: conduction band, valence band. So in conduction band and valence band, in bulk materials, all the energy levels are continuous energy levels. But in case of nano size, in terms of when it comes to nano size, so the energy levels are quantized. And also we can say that it is a discrete energy levels. Okay, discrete energy levels. So that's what here we are mentioning. So as discrete energy levels and enhanced surface activity. So because of this discrete energy levels and higher surface area, so the reactivity is much more in terms of in case of nanomaterials when compared with macro sized particles. Okay, then these changes create materials with tunable, superior, or entirely novel functionalities. So because of the change in energy levels, because of the change in energy band gap, because of the change in surface area, because of the change in surface area, these materials bring new functionalities, new properties. Okay, new properties. That's why. And also all these properties, whatever we are observing at nano level, so they are all tunable. They are all tunable. We can tune the properties, we can modify the properties, we can enhance the properties, right? So nanoscale phenomena are harnessed in energy, electronics, catalysis, biotechnology, and sensing applications. Okay, sensing applications. We are already seen the applications of nanomaterials in different areas. Okay, in different areas. We have seen, so in energy related applications like energy storage devices like supercapacitors, batteries, and also energy conversion devices like solar cells. We have seen in electronics, in display technologies, in sensing applications, right? So in biotechnology, biosensors, okay, and also we have seen in medical applications, in targeted drug delivery systems. So nanomaterials find applications in many areas of the today's world. Okay, so this lecture explores how each property when it comes to physical properties, chemical properties, optical properties, and electrical properties, which parameters, which properties are changing, when a material comes from macro level to nano level. Okay, macro level to nano level. So what kind of properties are changing, what kind of new functionalities are coming when it comes to nano scale. Okay, so that's what we are going to discuss in this lecture. Okay, so this lecture explores how each property, physical, chemical, optical, and electrical, evolves from macro to nano dimensions. Okay, macro to nano dimensions. Okay, right. So before going to discuss about this the individual properties, so we already familiar with the surface to volume ratio. So I will briefly touch up on surface to volume ratio, so those who are watching this video directly, so that they can understand these basic things to for more clarity of the change in properties. So that's why, so even I discussed this topic in depth in our previous lectures, but for those who directly watching this video, so it is helpful for them, so that's why I'm repeating. So those who are familiar with this concept, you can forward this video to the to directly to the physical properties of the materials. Okay, so those who are watching first time this video, so you have to be careful, because this property is the major reason for the new functionalities at nano level. Okay, right. Surface to volume ratio, the foundation of nanoscale behavior. The foundation of nanoscale behavior. See, if you see this one, it is a bulk material. Okay, it is a bulk material. So bulk material has less surface area. Why? Because if you take a bulk material, the surfaces are limited. The surface is limited. Okay, so that the surface is limited. So only less surface is exposed to the surrounding environment. To the surrounding environment. But whenever you cut this bulk material into number of pieces, see like this number of pieces, so that many faces or will come into picture. Many faces are ready to interact with the surrounding medium. So that's what that is the reason to increase the surface area. So if you see the individual particles, it can spread over more surface. Okay, more surface. So if you see this, so it can cover only this much surface. But if you make it into small number of pieces, so that these pieces can spread over large surface. Okay, so that's why, so the surface area increased when it comes to bulk to nanoscale. Okay, see here. So see some of the major points related to surface to volume ratio. As particle size decreases, see, very important point. As the particle size decreases, the surface to volume ratio increases dramatically. Okay. So what is happening here? The particle size is reducing. The particle size is reducing. So at bulk, so at bulk stage, the particle size is large. So as the particle size increasing, see here. So this is the bulk size, bulk particle, and this is the nanoparticle. So if you compare the size, it is very much smaller. Okay, very much smaller. So that's why. So as the particle size decreases, the surface to volume ratio increases dramatically. Okay. So in macro scale materials, most atoms are in the bulk. Okay, in macro scale material, most atoms are in the bulk. In nanomaterials, a large fraction resides on the surface. This is important. See, if you take a macro material, so most of the atoms are within the material. Most of the atoms are within the material. So only a fraction of atoms, only a fraction of molecules are on the surface. So limited atoms, okay, limited atoms are on the surface because of the because of the less surface area, because of the less surface area. But when it comes to nanoscale, so all the particles are very small in size. So most of the atoms comes onto the surface of the particle. So that's why in macro scale materials, most atoms are in the bulk material. But in nanomaterial, see, a large fraction resides on the surface. On the surface. See here, most atoms are in the bulk material, inside the bulk material. But in nanomaterials, so most of the atoms are on the surface or on. This is the main reason for most of the new properties or changes what we are going to observe in physical and chemical whatever the properties. Okay, it plays a major role. Right. This leads to increased reactivity, catalytic activity, and altered thermal and mechanical stability. So the reason is surface to volume ratio. So because of the most atoms present on the surface, so it brings increased reactivity. It brings catalytic activity, and also it can alter thermal and mechanical stability. So high surface area enhances adsorption and ion exchange. Okay, high surface area enhances adsorption and ion exchange, crucial in sensors and drug delivery. So because of this high surface to volume ratio, or because of this high surface area, so we can find applications in sensor technologies, okay, in biosensors, in many kinds of sensors, okay. So gas sensors, biosensors. So and also we can find in applications in drug delivery also, okay, in drug delivery also, okay. So likewise, surface atoms possess unsaturated bonds contributing to high surface energy and reactivity. Because of the most of the atoms are on the surface, we can have more surface energy. Okay, we can have more surface energy. Such behavior is harnessed in nano catalysts, energy storage, and environmental remediation. So we already seen that these nanomaterials can be used in many applications in energy, environmental, and catalysis. So many applications, environmental remediation also. Surface dominated behavior explains why nanoparticles behave more reactive surfaces than inert solids. Okay, because of this surface dominated behavior, because of the more number of atoms on the surface, and because of this high surface energy, so these nanomaterials are more reactive than any micro size particles or macro size particles. Okay, so the main reason, one of the reason, okay, one of the two reasons. Second one is quantum confinement, which will discuss very soon. So this surface to volume ratio plays a major role. Okay, so whenever we want to make a nanomaterial for any application, so our prime focus must be on making the material with high surface area. High surface area. High surface area provides high surface energy. High surface energy provides high reactivity. Okay, higher participation, so that we can so that all the properties will enhance as per our desired application. Okay. So this is about surface to volume ratio. Okay. So next, yeah. So this is the second reason for the new functionalities at nano scale. Okay, that is quantum confinement. Okay, quantum confinement, size controlled electronic behavior. Okay, So this quantum confinement plays a major role in changing the optical properties and electronic properties. Okay, optical properties and electronic properties. Okay, see here you can see, so this is a bulk crystal or bulk material. So in bulk material you can see the continuous energy levels, so that's why it is completely colored. So this is valence band and this is conduction band. So you can see the completely complete colored because of continuous energy levels. Okay, so this is the band gap, right? The energy gap between valence band and conduction band is the band gap. Okay, so then, so when you reduce the size of the particle from macro to micro to nano, what will happen? You can see in nanocrystals, nanomaterials, you can see the discrete energy levels, okay, the quantized energy levels, and also, so as the size is reduced, the band gap, you can see the band gap is increasing. Okay, so the band gap is increasing. Okay, so this is quantum confinement. Okay, quantum confinement. And also in our previous class we have discussed about this confinement in different nanomaterials, different nanomaterials. Okay, right, we will see some of the points related to quantum confinement. When dimensions shrink below the exciton Bohr radius, electrons and holes become spatially confined. Okay, so what is exciton Bohr radius? So the average distance between electron and hole in any exciton or in any electron hole pair. Okay, in any electron hole pair, so the average distance is approximately average distance in the exciton can be considered as Bohr radius. So whenever the size of the particle reaches to that small level, that small size, so we can observe this quantum confinement. So this leads to quantization of energy levels, unlike continuous bands in bulk materials. So as we said earlier, so in bulk materials we can find continuous energy levels. Okay, continuous energy levels, but in nanomaterials, okay, in nanomaterials, so we can see that the energy levels are quantized, discrete energy levels. Okay, as size decreases, the band gap energy increases. Okay, band gap increases, leading to tunable optical and electronic properties. So right, so because of the band gap, so most of the optical properties and electrical properties depends on the energy band gap. Okay, so but here as we're decreasing the particle size, so we can tune the band gap, right? We can tune the band gap. So because of this tunable tunable possibility, so we can play with the optical properties, we can play with the efficiency. Okay, then in quantum dots, yeah. In quantum dots, different size emits different colors in application of this principle. So because of this change in band gap, due to the size reduction, okay, due to the size reduction, so due to the size reduction, so what else changing? Because the optical properties will change, right? So different size nanoparticles, different size nanoparticles will display different colors. Okay, so see here, so this is the size red particle. So this is the size of the particle, this is the size of the particle. See, the size of the particle is reducing. So as the size of the particle is reducing, what happens to the band gap? Band gap is increasing. Along with the increase in band gap, the color also changing. Okay, the color also changing. So this is what we are using in our display technologies. So so we need to alter the size of the particles to emit different colors. Okay, so that's what here we mentioned. In quantum dots, different sizes emit different colors, an application of this principle. Okay, different sizes emit different colors. Okay, then nanoscale semiconductors, thus enable color specific bioimaging and photodetectors. Okay, nanoscale semiconductors thus enable color specific bioimaging. Okay, color specific bioimaging and photo detectors. So based on, see for example, if you see some of the images, so we need to give properly colored images so that we can make color contrast. Okay, color contrast to different parts in images. Okay, so for that we need these nanoscale semiconductors. Okay, then electronic density of states, okay, DOS, becomes discrete, drastically affecting conductivity and absorption. So because of the change in this band gap, it directly affects absorption, emission. Okay, absorption and emission, and also conductivity. Absorption, emission and conductivity. So because of these properties we can tune optical properties and electrical properties. Okay, so these effects revolutionize applications in optoelectronics, photovoltaics and photons. Okay, and photons. So this is about quantum confinement. Quantum confinement is, in quantum confinement we need to understand that as the size reduced, band gap is increasing. As the size reduced, uh, the energy levels become discrete and quantized. As the size reduce, the color of nanoparticle will be varied. Okay, so these phenomena plays a major role in optical and electrical properties, particularly absorption, emission and conductivity. Okay, then so now we will see physical properties. Okay, physical properties. Okay, so I will just move this image. Okay, right. Okay, so we will see physical properties. So here you can see this is the property. So what kind of how many types of properties related to physical properties changing. So as the size reducing from macro to nano, macro material to nanomaterial, so all these properties are changing. Okay, all these properties: mechanical strength, hardness, elastic modulus, ductility, melting point, density, surface energy, surface tension, thermal conductivity, heat capacity, diffusivity. So in all these properties, we can find change when a material comes from macro size to nano size. Okay, so there are many more. So we will focus mainly on this. So in this slide, you can see what is changing at nano level. Okay, what is changing at nano level, and also at this column, you can see excuse me. At this column, you can see the advantage. So because of this change, what is the advantage? What is the advantage we are getting? Okay, and also because of this advantage, so what kind of applications? What are the applications? Where do we use this advantage? Okay, so we are seeing like this. Okay, right. The first property is mechanical strength increases. What is the change at nanoscale in mechanical strength? So mechanical strength increases due to grain boundary strengthening. Okay, so this property, so grain boundary, in terms of grain boundaries, so we will get the positivity advantage. Okay, so because of this increase in grain boundary strengthening, so we can get higher durability. Okay, higher durability and wear resistance. Okay, so high, anyway, whenever we make any material, so we wish to uh, use that material for long time, right? For long time. So that is durability, right? So because of this change at nano level, we can have higher durability in the material. So because of higher durability and wear resistance, we can use these particular nanomaterials in aerospace applications, nano coatings, micro electromechanical systems, MEMS. Okay, so for example, whenever we make any, for example, transport vehicles, let it be a car, let it be an aeroplane, so the material, it should not, it should be rust free, right? So and also it should, because these vehicles have to work in on the day, in hot summer, in and also in winter, too much cold winter. So it has to, it should have durability, right? It should have durability because it works in very harsh conditions, right? In a very harsh, tough conditions, tough situations, in tough weather conditions. So because of this higher durability nature, so these materials can be used in aerospace materials and also nano coatings. Whenever you coat this nano coating, for example, this material, if you coat on a surface of a car body or aeroplane body, so it gives strength, right? So it makes the material more durable. Okay, and also hardness. The second one is hardness. Okay, so typically increases in nanocrystalline materials. So hardness also increases in nanocrystalline materials. So the hardness in macro size, in macro materials, and also if you compare hardness in nanomaterials, so the hardness will increase in nanocrystalline materials. So what is the advantage we are getting due to the increase in hardness? So it improved scratch and wear resistance. So it cannot be easily scratchable. Okay, it cannot easily scratchable. So because of this advantage, so these materials can be used in hard coating for tools and also armor plating. Hard coating for tools. So whenever same things, we can use it in coating car bodies and aeroplane bodies, and also on, for example, um, mobile phones. So whatever these surfaces, okay, right? So we can apply these materials. So hardness will change, and also elastic modulus. Okay, elastic modulus may increase for example, if you take example, in carbon nanotubes have extremely high modulus, so it gives more toughness. Okay, so structural ability at lower weights. For example, if you take, it is lightweight, yet it provides very good strength, right? Very good strength, right? So and also lightweight composites for aerospace and automobiles. So as we said earlier, as we discussed, So it provides lighter weight so that it can it consumes less fuel. Okay, it consumes less fuel. So and also it provides higher strength. Okay, lightweight composites for aerospace and automobile applications. And also here you can see ductility often decreases due to dislocation confinement, enables super strong and hard materials. Okay, super strong and hard materials. So where do we can apply this? In nanoceramics, protective wear resistant films. Okay, I think like in mobile screen guards. Okay, so it provides super strong and very hard materials. Okay, hard yet super sensitive. Okay, so and also melting point. So melting point definitely decreases when you bring the material down to nanoscale. Okay, so that means if a material melts at 100 degrees centigrade, so if you make the same material with nano size, so then the melting point will come down from 100 to 80 or 60 or 70 like that. Okay, so based on the materials. Okay, so the melting point decreases in nanomaterials. So it is easier to process or sintering at lower temperatures. If you want to bend a material, so you need to melt, you need to heat up to very high temperature. But if you make the material with nano size, so even at low temperatures, you can bend it. Okay, you can tune the shape whatever you want. Okay, right. So it is easier to process or sinter at lower temperatures. So what is the application? Low temperature sintering, nano soldering in electronics. Okay, so it is very advantage. And then density. So slightly altered due to porosity, surface atoms and defects, right? So out of the four dimensional materials, so which has more porous? So usually three-dimensional materials, right? So usually 3D material have uh, more possibility to have porous structure. Okay, because of this porous structure, so what's happening here? So the density is changing. Okay, slightly altered due to porosity. So tuned mass properties, we can see within a particular volume. So because of this porous structure, so we can change the mass loading. Okay, we can change the mass loading. So this can be used very useful in nanoporous materials for catalysis applications, in filtration applications also. Okay, so this is. And then surface energy, so we have discussed it, right? So nanomaterials provides high surface area, right? High surface area, high surface energy, right? So this surface energy increases significantly due to higher surface area, because bulk materials surface area is less. So most of the atoms are inside the material, right? But in case of nanomaterials, all the atoms comes to the surface, so that surface energy is more. So what happens? What is the advantage? Enhanced chemical reactivity. So more atoms on the surface, so that more participation, more reactive with its surrounding environment. Okay, so enhanced chemical reactivity. So then what are the applications? Catalyst, energy storage, right? So energy storage example, lithium ion batteries, supercapacitors, you can see. And also surface tension. So what happens to the surface tension? It increases at nanoscale. What is the advantage? Greater control over wetting nature. Okay, for example, if you see in nature, lotus leaf, right? So it cannot wet on the surface. So it is useful at the self-cleaning glass doors. Okay, self-cleaning uh, glass. So for example, if you find a tall buildings, okay, skyscrapers, so it is covered with glasses, right? Covered with glasses. So if you coat with nanomaterial, so all the glasses, so no need to clean with water, no need manpower, right? So it has self-cleaning nature. So whatever the dust particles deposited, it slides down immediately. Okay, so that's what it is. Okay, greater control over wetting. Nano fluids. Where do we find applications? Nanofluids, inkjet printing, drug delivery systems. So we can find these applications. Okay. Then see here. See the properties. Thermal conductivity. So thermal conductivity can increase or decrease. Okay. So we can tune controlled heat flow pathways. So applications: nano thermal insulators, thermal interface materials. Then heat capacity. Deviations at low temperature due to phonon confinement. So where do we have, what are the advantages? So better energy storage and dissipation control. Where do we have cryogenics and thermoelectric cryogenics? Where do we apply? Where do we see cryogenics? In rockets, right? In rocket technology. Okay, so we use cryogenic engines, right? So and also diffusivity increases significantly. So faster atomic mobility and reactions. And so the applications: sintering, catalysis, nanoceramics, and manufacturing. So all these properties will change. So these are the properties, and this is the change at nano scale, unlike macro size. So these are the advantages we are getting, and these are the applications. So this is about glossary of physical properties. Okay, physical properties. So you see, you can see, so many properties are changing. So what are the reasons for all these changes? Two reasons mainly, right? So one is surface to volume ratio, and the second one is quantum confinement. Okay, quantum confinement. Then chemical properties. Okay, chemical properties. Same, these are the properties, and this is the particular change at nanoscale. This is the advantage, this is the application area, and examples. Okay, and examples. So just pause the video and see this slide. Okay, so these are the chemical properties. Chemical reactivity significantly increases due to high surface atom density and surface energy. Okay, so what is the advantage we are getting? Faster and more efficient reactions. Okay, more efficient reactions. So because most of the atoms are on the surface, so every atom will participate in reaction, so that it has faster and efficient reactions. So what are the application area? Catalysis, energy, environmental. Okay. So example of applications: nano catalyst in fuel cells, CO oxidation, water splitting. Okay. So in water splitting, in dye degradation, Wait a second. Okay. So the next one is redox behavior. Altered redox potential due to quantum confinement and surface state shifts. What are the advantages we are getting? Tunable oxidation reduction reactions. Okay, tunable oxidation and reduction reactions. So because the efficiency was decided by redox reactions. Okay, redox reactions. So the participation. So applications, energy storage, sensing. Examples of applications, electrode materials in lithium ion batteries and supercapacitors. Okay, so this is redox reactions are very important in catalysts and also in energy storage purpose. Then solubility and dispersibility. Okay, solubility and dispersibility often enhanced in polar non-polar solvents due to surface modifications. Surface modifications. Okay, advantage, easier processing, improved interaction with biological systems. Okay, in biological systems. So applications, biomedical, drug delivery. Okay, examples, drug carriers, nano dispersions in pharmaceuticals. So whenever some person take a medicine, it should flow easily, it should disperse easily within our body. Okay, and also if it is a targeted drug delivery case, so it has to flow easily, it must flow easily to the affected area where we want the medicine to go. Okay, so that's why solubility and dispersibility is very important in case of biomedical applications. Okay, then surface functionalization. How can what is the advantage of functionalization? So by doing functionalization, so we can add more different molecules to the surface of the nanoparticle, so that it can effectively interact with the surroundings based on the requirement and the purpose. Okay, so because of the this change in surface functionalization, what is the change at nanoscale? Increased capacity for surface functional groups or coatings. Okay, so we can increase the surface energy, we can increase the capacity. Okay, so then what is the advantage? Tailored surface chemistry for selective interactions. Because of the surface nature, so some nanoparticles can interact with some surroundings. Okay, so that can be tuned by the functionalization. Okay, so by doing the proper functionalization, so depends on the requirement. So depends on the requirement, we can modify the surface with this functionalization, and it brings many advantages. Okay, so these advantages, so we can find in biosensing, in targeted delivery, targeted drug delivery. So examples, antibody functionalized gold nanoparticles for cancer detection. Okay, for cancer detection in biomedical field. So this particular property has advantages. Okay, then corrosion resistance. So may increase or decrease based on surface passivation and morphology. Okay, based, and the advantage is controlled corrosion and for desired environments, biomedical implants, coatings. TiO2 nanocoatings for corrosion resistant orthopedic implants. So for example, if somebody got an accident, something was broken, and then so we usually heard some steel plates or rods can be inserted in the body, right, in the body. So if that material has corrosion property, corrosion nature, but so that it will make more damage, more damage. So we need to implant material which should has corrosion resistance, right? It should be more durable, right? So that's what it is. So in biomedical implants and also coatings, so we need this nature, corrosion resistance. So the material must have corrosion resistance. So and then what is changing? Photocatalytic activity. So how can this photocatalytic activity can be increased? Hmm? So just by tuning the band gap. So it is greatly enhanced due to band gap tuning and high surface area. So efficient light driven reactions. Because of this nature, so these materials can absorb more sunlight, right? Can absorb more sunlight because of the tune band gap. Okay. So and then application area, environmental, renewable energy. So these areas we can find the applications. TiO2, zinc oxide, nanoparticles in light degradation, and hydrogen generation. Okay, hydrogen generation. Then chemical stability. Some nanomaterials become less stable. Some nanomaterials become less stable due to high surface energy and oxidation tendency. So it can be stabilized through functionalization. By applying functionalization, we can tune this. So where do we apply? Where do we find the applications? Packaging technology, in coatings, and in electronics. Then examples: silver nanoparticles in antibacterial coatings with surface capping agents. Okay, with surface capping agents. Then we can change the acidity and basicity. Okay, we can change the pH. Okay, so advantages: what are the changes? Surface acid base strength changes due to size and coordination environment, right? So by changing coordination, by changing the surface, we can change the pH. Then enhanced catalytic selectivity and activity, petrochemicals, green chemistry. And then examples: solid acid nanocatalysts for alkalization, esterification, and reactions. So these are the application area. Okay, and also reaction kinetics. So these are all the chemical properties. Okay. Then, so what are the key changes and benefits regarding chemical properties? Okay, chemical properties. So what the main mechanism? High surface to volume ratio. Why it happens? More reactive atoms exposed at the surface. Okay, more reactive atoms exposed at the surface. Okay. Key benefit: increased chemical activity and surface reactions. Okay. Then quantum size effects. Quantum size effects bring alters energy levels and electronic structure. Key benefit: tunable redox reactions and also optical properties. Then surface defects and curvature. Why it happens? Because it enhances active sites and reactivity. Key benefit: effective heterogeneous catalysis. Tunable surface chemistry. Okay, tunable surface chemistry. Surface can be engineered with ligands or functional groups. Selective binding compatibility with biological systems. Okay, with biological systems. And then you can see the application areas overall with examples. So we are this chemical properties we can find in different fields: energy, environmental remediation, biomedicine, sensing, coatings, and paints, in catalysis also. So just pause the video and see the advantages and examples. Okay. Okay, so this is about chemical properties. Then we will go further. Yeah, this is about optical properties. Okay, optical properties. See, you have to understand every property, how it is changing, and what kind of change it is bringing when it comes from macromaterial to nanomaterial. And you should also understand the proper advantage. Because of that small change, what is the advantage we are getting? And with this advantage, so where do we find applications? So in which application area, so this advantage can be useful. So that's why we should understand every basic property. Okay, right. So, yeah, absorption spectrum broadens and shifts, redshift or blue shift, due to quantum confinement effect, right? So this, because of this quantum confinement effect, we can tune band gap. So by tuning the band gap, we can tune the absorption range of sunlight. Okay, so some material can absorb only UV light, some material absorb only visible light, right? Some materials can absorb UV and visible light, right? So our intention is to capture as much as possible of sunlight. Okay, maximum sunlight absorption. So for that purpose, so we need to tune the band gap, which suitable to the suitable to absorb more sunlight. Okay, so that's what it means. Broadens and shifts. Okay, then what is the advantage? Tunable absorption for specific wavelengths, for specific wavelengths. And also sometimes we need particularly blue light, particularly red light. So for that purpose also we can tune the wavelength. Okay, we can tune the wavelength. Okay, so what are the applications? Solar energy and photo detectors. Okay, solar energy, photo detectors. So usually quantum dots in multi-junction solar cells, and also lead sulfide quantum dots in IR detectors. Okay, so in this area, in solar energy and photo detectors, so this particular property, absorption spectrum and its tunability, having more advantages. Then emission spectrum. So the first point related to absorption, and the second property is emission spectrum. Okay, emission. So photoluminescence. So photoluminescence also, it is heavily dependent on size of the particles. Okay, size of the nanoparticles. So it becomes size dependent and sharper. Okay, size dependent and sharper. So broadening spectrum are also sometimes it is very sharp peaks. Okay, photoluminescence. So what are the advantages we are getting here? Color tuning for optical displays and biological labeling. Okay, biological labeling. So where we are, what are the application areas? Bioimaging, LEDs, and display technologies. Okay, display technologies. So at present our monitors, mobile phones, or televisions. So any big screens. Okay, so and also cadmium selenium zinc sulfide quantum dots for RGB display, pixels and fluorescent tagging. Okay, so these are all applications. Okay, so the next property, refractive index. Refractive index varies due to size and shape. Okay, size and shape. Yeah, refractive index varies due to size and shape, often becoming anisotropic. So what is the advantage? Enhanced light manipulation. Okay. So application area, metamaterials, photonic crystals. Okay, photonic crystals. So examples, nanostructured photonic materials with engineered light paths. Okay, with engineered light paths. Okay. Then surface plasmon resonance, SPR. So this surface plasmon resonance usually observed in metals, okay, like copper, gold, silver. Okay, enhanced SPR in metal nanoparticles. Okay, Then, so what are the advantage? Strong light matter interaction and signal amplification. Signal amplification. Application area: sensing, imaging, photothermal therapy. Photothermal therapy. Applications: example of applications: gold nanoparticles in biosensors, plasmonic heating for cancer therapy. So usually this metal nanoparticles find uh, in biomedical applications. Okay, in biomedical applications, particularly sensing and this cancer therapies like this. Next one, scattering. Increased Rayleigh and Mie scattering in specific size ranges. So, what is the advantage? Enhanced contrast and light diffusion. Application area: sensors, optical coatings. Examples: titanium dioxide or SiO2 nanoparticles in sunscreens and diffusive Diffusive films. For example, so you will use sunscreen lotions, right? Sunscreen lotions. So when you apply sunscreen lotion on your skin, so what it will do? So it will reflect the UV light into the air. Okay. So it will protect our skin. Okay. And then transparency. So you will find this transparent glass doors, right? Transparent glass doors or glasses on buildings, right? In buildings. So usually if there is no glass, so all the light, if it is a normal glass, so all the light with radiation with heat enters into the room. But if you make a coating, nano coating on this glass, so it will reflect the incident UV rays into the air, so that the room can be, it's not that much heat. Okay, heat. So it provides transparency and also it provides this coolness. Okay, so right, see here, becomes transparent due to reduced grain boundaries and scattering. This is the reason, because of this it provides this property. Clear conductive coatings and films. Okay. Applications: electronics, smart windows. Examples: ITO, indium tin oxide, ITO nanoparticles in transparent electrodes. See, for example, we will make ITOs and FTOs. So it is a transparent and also conductive. Okay, transparent and conductive. Then non-linear optical response applications, photothermal conversion applications, property, and also fluorescence lifetime applications. So just to go through all this. Yeah. Then optical properties. What are the key changes and mechanisms? Key changes and mechanisms. Mechanism: quantum confinement. Why it happens? Discrete energy levels form as electrons are confined. Okay, so because electrons are confined, discrete energy levels are forming. So out of this, what is the resulting change? Tunable emission and absorption. So because of this mechanism, this is happening, and this is the result. Okay, this is the result: tunable emission and absorption. Then surface plasma resonance. Why it happens? Because collective oscillation of surface electrons in metallic nanoparticles. Okay, so usually this property can be observed in metal nanoparticles. Okay, metal nanoparticles. So collective oscillation of surface electrons in metallic nanoparticles. So what is the resulting change? Intense light absorption, scattering at specific wavelengths. Scattering at specific wavelengths. Okay. Next, high surface area, more active optical sites. more active optical sites. Change enhanced photoluminescence and light matter interactions. Okay, enhanced photoluminescence and light matter interactions. Then last one, reduced dimensionality. Okay, reduced dimensionality alters light propagation and scattering behavior. Okay, scattering behavior. So what is the change? It controls over reflectivity, transmission and refractive index. Okay, it controls over reflectivity, transmission and refractive index. So these are the main mechanisms related to optical properties, and these are the changes at nanoscale, and these are the, so because of this is the reason and this is the result. Okay, mechanism, reason, result. Okay, so just go through all this. See the fields in optical properties: biomedicine, energy, display technology, sensing, photonics, optoelectronics, catalysis. So these are the fields, right? These are the fields. So particular, what is a particular advantage related to this field? Tunable fluorescence and SPR. Okay, examples: quantum dots for tumor imaging, gold nanoparticles for biosensing and therapy. Okay, so quantum dots are useful for imaging to give proper color contrast, and also energy field. Energy, enhanced light absorption and scattering, nanostructured TiO2 in dye sensitized solar cells, DSSC. Okay, so this is the field advantage. Example: display technology, bright tunable emission with long lifetimes. Examples: quantum dots in QLED TVs. Okay, quantum dots in QLED TVs. Then sensing field, sensors. So SPR based signal amplification. Examples: LSPR biosensors for DNA protein detection, biomedical application. Okay, biomedical applications. Then optoelectronics, light manipulation and linear response. Okay, examples: photonic crystals, optical switches, optical switches. So this can be used in lasers. Okay, so we can use this property in lasers and photonics. Catalysis, photothermal effect and light triggered reactions. Okay, light triggered reactions. So what are the examples? Plasmonic nanoparticle catalyst for light driven chemical reactions. So these are all the optical properties. Okay, optical properties. Okay, so far we have discussed physical properties, chemical properties and optical properties, and the last one is electrical properties. Okay, electrical properties. Yes. See the electrical properties. So what properties are changing here? We are focusing on conductivity, electron mobility, quantum conductance, tunneling current, dielectric constant, work function, band gap, charge storage capacity. Okay. So coming to the conductivity, so what is changing at nanoscale? Conductivity can either increase or decrease due to surface scattering and grain boundary effects. So we can alter anyway. Okay, so we can increase or decrease. Okay, it can. So what is the advantage we are gaining here? So tailored conductivity for miniaturized devices. So based on our requirement, based on our power requirement, so we can tune the conductivity. So depends on our requirement, depends on our desired efficiency. Okay. So what are the application area? Nano electronics and sensors. Nano electronics, sensors. What are the examples? Silver nanowires in flexible transparent conductors. So in your flexible mobile phones, fold phones, and also smartwatches with flexibility. Okay, so and many more. So in also in sensing applications, some sensors we can put on screen. So for example, to find out the fitness of any athlete, so they can put some sensors, right? Some sensors while they work out. Okay, in gyms. So such kind of sensors, in sensors we can use these materials. Okay. So next, electron mobility. Okay, electron mobility. So it reduced due to enhanced surface and grain boundary scattering. Advantage: high speed switching in short channels. Application area: transistors, logic gates. Examples: carbon nanotube, graphene based devices. Okay. So because these transistors and logic gates with high speed switching is very important for computing applications also. Okay, so we can use in that way. Then quantum conductance become quantized, so in one dimensional systems. So what is the advantage? Enables ultra low energy electronics. Application area: quantum computing, nano transistors. Quantum computing, nano transistors. Examples: single atom wires, quantum point contacts. Okay. Then tunneling current, significant at nano gaps and thin barriers. Okay. So and then dielectric constant can be size dependent and vary due to surface effects. What is the advantage? Enable design of high K dielectrics for capacitors. Application area: energy storage, nanocapacitors. Okay, ultra capacitors. Examples: barium titanate nanostructures. Okay, so this is about dielectric constant. And coming to work function. So change at nanoscale, work function altered due to surface reconstruction and size. Okay. So advantage: tunneling electron emission and barrier, catalysis and vacuum electronics. Examples: nanostructured electrodes in fuel cells and field emitters. Okay, so a work function is very important in designing nanomaterials for various applications. Okay, then band gap. So band gap is very important for absorption, emission. Okay, so this can be tuned by quantum confinement, right? Quantum confinement. So application area: LEDs, photodetectors, solar cells, zinc oxide, cadmium selenium, lead sulfide quantum dots. Charge storage capacity. Okay, so charge storage capacity can be increased due to high surface area and also porous structures, right? So three-dimensional material offers very good porosity, okay, so that it can store high energy and power density. Okay, so best examples: application area: supercapacitors, lithium ion batteries. Okay, supercapacitors, lithium ion batteries. So and then, so examples: MnO2 nanosheets, RGO based hybrid electrodes, and also many carbon related carbon nanotubes, right? So this is about electrical properties. So yeah, then check this slide. See the properties. See the properties. Okay. Mechanism, explanation, impact. Okay, so what is the mechanism? Quantum confinement. Okay, quantum confinement. Explanation: energy levels becomes discrete due to spatial confinement of electrons. Okay, impact: alters band structure and charge transport because of quantum confinement. So this energy levels are discrete, quantized, and the electrons are confined to a particular direction, particular region. Okay, so because of this confinement of electrons, so the band structure alters and band gap changes, and also the charge transport also. Then second one: surface to volume ratio. Okay, surface to volume ratio. So dominance of surface atoms alters carrier scattering and energy barriers. What is the impact? It affects conductivity and charge trapping. Okay, charge trapping. Electron tunneling. Explanation: electrons can pass through barriers thinner than 2 nanometer. Thinner than 2 nanometers. So what is the impact? It enables non-classical current flow. Okay, it enables non-classical current flow. So where do we see this electron tunneling? So we have seen in previous classes, right, in SEM images and TEM images. So where we need this electron tunneling effect. Okay, electron tunneling effect. So how this SEM operates? This SEM, it scans the surface by using this phenomena, electron tunneling. See, this electron can pass through barriers thinner than 2 nanometer. If it is, this barrier is less than 10 nanometers, these electrons can transfer from one side to another side. Okay, so that is electron tunneling. Okay, so then Coulomb blockade. So energy required to add an extra electron becomes significant. So what is the impact? Useful for quantized current and digital logic at nanoscale. So it is useful in nanoelectronics. Okay, so this is about the electronic properties. We will see the application areas in electrical properties. Okay, see this slide. I'll explain. Now you understood the basic phenomena like surface area, quantum confinement, changes. You should understand the importance of every property change. Okay, every property change. So then only you can search the application. Okay, you can find the application. See in nano electronics. Okay, in nano electronics, nanoscale electrical advantage. Nanoscale electrical advantage. Low power consumption. Low power consumption. Faster switching. Faster switching. Examples: CNTs, carbon nanotubes. Energy storage, high capacitance and faster charging. Okay, so this is the advantage. So with this advantage, you can use supercapacitors with porous nanocarbons, hybrid electrodes. Okay, hybrid electrodes. In sensors, high sensitivity due to enhanced charge interaction. Examples: graphene and zinc oxide nanowire gas sensors, FET based biosensors. Then photovoltaics. Advantage: tunable bandgap and improved charge separation. Examples: quantum dot solar cells, perovskite nano hybrid solar cells. These are the examples. Next, flexible electronics. Okay, flexible electronics. High conductivity with mechanical compliance. Examples: silver nanowire, graphene hybrid electrodes for wearables. So for wearable smartwatches, wearable sensors. Okay, so then quantum computing. So it is the advanced technology, so which is still in R&D stage. Control over single electron transport, qubits in quantum dots, Josephson junction arrays. So usually for digital computing, we are using 0 and 1 as a quantum bits, right? Sorry, uh, classical bits. But here in quantum technology, so we will use the waves, particle light, right? So this is about quantum computing. Okay, so in this session, we have seen, yes, properties of nanomaterials, right? Properties of nanomaterials, particularly physical properties, chemical properties, optical properties, and electrical properties. Okay, so this is about macro to nano. Okay, macro to nano. This is about surface to volume ratio. Okay, surface to volume ratio. This slide is about quantum confinement. Okay, quantum confinement. This is about physical properties. Okay, physical properties, chemical properties, optical properties, and electrical properties. Okay, I hope this session uh, helpful to you. Please share this video with your friends and students. and like this video. And if you have any doubts related to this nanomaterials and nanotechnology, yeah, you can comment here. I will definitely reply to you. And also please share this video with your student friends and who is working in this research area. And these lectures are helpful to physics and chemistry lecturers, and also those who are working in this research area. So I hope you like this video. So we'll see you next time. So next time I will come up with energy storage devices. Uh, so see you next time. Thank you. Thank you. Thanks for watching this video. Hello everyone. Welcome to the nanomaterials lecture series. So in this session, we are going to discuss about energy storage devices. Hello everyone. Myself, Dr. Babu Battula, Professor and Dean, School of Sciences and Humanities, SR University, Warangal. So in our previous lectures, we have discussed about nanomaterials. What are nanomaterials? How can we make macro materials into nanomaterials? What are the properties of nanomaterials? What are the reasons for the properties at nano level? So we have discussed the fundamental principles like surface to volume ratio, and also about quantum confinement. And also we have discussed about classification of nanomaterials from zero-dimensional materials to three-dimensional materials. We have discussed many things. So if you didn't watch my previous videos, you can go and watch all my previous videos related to this nanomaterials lecture series. So in this session, we are going to discuss about energy storage devices, particularly supercapacitors. Okay. Yeah. So why do we need energy storage? Why do we need energy storage? What are the ways to store the energy? How many types of energy resources are available to us? So we will see all these possibilities in this session. First, we will see about types of energy storage, then capacitor versus supercapacitor, difference between energy and power density. We will see the difference between supercapacitor and a battery, and also finally the advantages of supercapacitors and applications of supercapacitors. Okay, so we are going to discuss about all these things in this session. So I hope you will learn some knowledge on this topic, energy storage. Here if you see this image, so you can see the types of energy sources available to us. Okay, if you see from start here, nuclear energy. So from nuclear reactor we can get this nuclear energy, and also natural gas. Okay, natural gas. Then solar energy, wind energy, hydro energy, hydropower. Then we will discuss about energy efficiency, system efficiency, transportation storage, and demand and supply response. So energy storage can be, we will get energy from all these sources. Okay, so this is the complete cycle for the production of energy storage, transportation of energy storage, usage of energy storage, right? Yeah. If you see this image, you can get the complete idea how can we produce, how many types of energy storages we need. Actually, why do we need energy storage? See, without energy storage, let's say without power, without current, so we cannot sustain a single day, because if you want to run your mobile phone, you need power. You need so you have a battery, and that battery requires power energy. If you want to run your uh, bike vehicle, you need energy. If you want to run any industry, any machine, you need energy, right? So we need, without power, we cannot, our daily life cannot went smooth, right? So, but can we produce instant energy for all our needs? Can we produce energy? No, we cannot produce energy instantaneously for all our needs. For all our needs, right? So we have huge energy demand, but we cannot produce instant energy to meet all our demands. For that purpose, we need to store energy. We need to store energy. Without storage of energy, without sufficient energy, we cannot run the our daily needs. That means from mobile phone to fan to vehicle to uh, to air condition, whatever, to industry. So from a two wheeler to aeroplane, whatever the transportation, be it a ship, be it a train, be it an aeroplane, be it a bus, be it a train, be it a bike, whatever it is. So for all transportation vehicles need energy, and also machines like industries, textile industry, medical industry, hospitals, schools, universities. So everything, everywhere we need energy. Everywhere we need energy to run our our needs. Okay, so but I said earlier, we cannot produce energy instantaneously to meet all our demands. So for that purpose, we need to store energy. So first we need to know from where we can produce energy. What are the ways, in how many ways we can produce energy? So first we need to focus on production of energy, and then with that production of energy, whatever the energy we produced, immediately we cannot use it, right? Immediately, so we cannot use all the energy that we produced. For example, if you take a nuclear reactor, if you take a nuclear reactor, so all the energy produced from nuclear reactor, we cannot immediately utilize all the energy instantaneously, right? So the energy production and also energy usage. See, this demand and supply is not same all the way, all the time, right? So whenever we have a chance to produce energy, we have to produce energy. So whenever we have a chance, for example, if you take a solar energy, okay, if you take solar energy, if you consider solar energy can be produced only on sunny day, only on daylight. We cannot produce solar energy on night, in night, right? So in daytime only we can produce solar energy. We cannot produce solar energy in night times, right? So in that case, for example, if a plant completely depends on solar energy, can that solar energy, can we produce at night to run that industry? to run that plant? No, it is not possible. So first we need to produce energy wherever, whenever it is possible. We have to produce energy. Then we need to store the energy. How can we store the energy? So that's what we are going to discuss in this session. So we need some systems that store energy, and then these so whenever we need energy, so we can withdraw energy from that energy storage system. Okay, so that's why energy storage is very very important. It is in between production and usage. Okay, production and usage. So in today's session, so let's see first here, so how many ways, what are the ways to produce solar energy. If you see here, solar, firstly solar energy. Okay, solar energy, wind energy, hydro energy, tidal energy, wave energy, geothermal energy, ocean energy. So these are all the energy sources. Okay, so by solar energy we can convert from photo conversion to photocatalytic energy, photoelectrochemical energy, photobiological energy, right? So, so these are all part of this energy storage system. Okay, energy storage system. Here also you can see types of energy storages. So this is the basic energy storage types, applications, categorization and comparisons. Okay, so out of the different types of energy storages, we can store energy as a electrochemical energy. Okay, electrochemical energy, thermal energy, thermochemical energy, flywheel technology, compressed air technology, liquefied air. We can store energy in all these forms: magnetic energy, pumped hydro, liquefied air, compressed air. So then applications, we can use this energy storage to various applications like general applications, energy utilities, for example, industries like this, then renewable energy utilization, buildings and communities, and also this energy can be utilized for transportation. Okay. Then categorization and comparisons. So technical performance, economies, advantages and disadvantages we can discuss. So out of all these parts, our prime focus is electrochemical energy. Okay, electrochemical energy. So that's where supercapacitors comes into picture. Okay. So out of this electrochemical energy, so we will discuss about capacitors, supercapacitors, batteries. Okay, right. So firstly, we will produce energy. This produced energy can be converted. For example, if you consider solar energy, solar panels convert solar light to electrical energy, right? Electrical energy. Here you can see some of the energy conversion methods. For example, this electrochemical energy conversion. Okay, electrochemical energy conversion. So fuel cells are useful to convert chemical energy into renewable energy. Okay, then electrosynthesis, renewable energy converted to chemical energy. So this is artificial photosynthesis. Okay, so here you can see the basic energy conversion methods. Electrochemical energy convert chemical energy into electrical energy. Okay, electrochemical energy. Then what is photovoltaic? Photovoltaics convert solar energy to electrical energy. Solar energy to electrical energy. Then thermoelectric. So thermoelectric energy means it convert heat energy into electrical energy. So these are the renowned energy conversion methods. Electrochemical means it converts chemical energy to electrical energy. Then photovoltaic, solar energy to electrical energy. Then thermoelectric, heat energy to electrical energy. Okay. Here you can see electrochemical methods. The electrochemical method is the only one which is commercial and has been for many years. The other methods are in various stages of research and developments. So if you see, for example, um, we cannot completely rely on solar energy, right? We cannot completely rely on solar energy. But in case if you store energy in electrochemical way, you can completely you can depend on, for example, if you nowadays we are familiar with electric vehicles, right? Electric vehicles. So in electric vehicles, most of the electric vehicles are run by lithium ion batteries, right? Lithium ion batteries, that means it is a proven technology and it is a commercially using technology. Okay, commercially using technology, that is the that's why this electrochemical methods are bit forward in terms of other energy storage technologies. Okay, other energy storage technologies. See this one, this in this picture you can observe energy storage. So this is a windmill and this is a solar energy. So the energy produced by windmills or the energy produced by solar panels, that energy can be stored in the form of electrochemical methods, that is in the form of batteries. Okay, in the form of batteries, and that energy can be easily transported and that energy can be used in many ways. Okay, used in many ways. For example, that electrochemical energy, and the beauty is here the energy is green energy. So the energy produced by the windmill is a green energy, and also the energy produced by the solar energy is a green energy, right? So this green energy can be stored as a chemical energy in a battery, and that energy can be utilized as electrical energy for many applications. Okay, for many applications. So right. So the conversion of chemical energy to electrical energy is one of the energy conversion methods collectively described as direct energy conversion. So the chemical energy can be directly converted into electrical energy. Okay. Since electrical energy is easy to transport, easy to use, and easy to control, it is favored as the terminal form of energy for transmission and distribution. So the most convenient way of energy is electrical energy that can be utilized in many ways for transportation, for maintenance, for any institutions, and also for industries, right? For transportation like buses and trains. So the electrical energy is most convenient way, and these electrochemical energy can be it is involved the conversion of chemical energy into electrical energy. So the energy stored as in the form of chemical energy and that can be converted into electrical energy, which is most convenient to utilize in many ways. Okay. So any device which can cleanly, efficiently and directly convert some inconvenient form of energy to electrical energy is of considerable interest. So that is what electrochemical energy. So electrochemical energy, so that is from chemical energy to electrical energy. Okay. Right. So now we will discuss about the basic electrical components which can store energy. Okay, which can store energy. So that is capacitors. Okay, capacitors. Capacitors are very basic and fundamental energy storage device. Okay, capacitors are simple passive device that can store an electrical charge on their plates when connected to a voltage source. Okay, so capacitors are very simple passive device so that store electrical that can store an electrical energy on their plates. Okay, so it is not electrochemical energy. Okay, so because the in the basic capacitor, it has parallel. The parallel plate capacitor is the fundamental capacitor. Okay, so in that parallel plate capacitor, the charge stored on the plates. Okay, the charge stored on the plates. Here you can see, yeah, here you can see. So these two are the plates, conductive parallel plates. Okay, the parallel plate capacitor is the simplest form of capacitor. So it is one capacitor, one parallel plate. This is another parallel plate. Okay, these two are parallel plates. So in between two parallel plates, we are placed a dielectric medium. Why? Because to improve the capacitance. Okay, capacitance. So without dielectric, the capacity is less. If you introduce dielectric in between parallel plates, the capacity will increase. Okay, so this is the charge, right? So what are the critical parameters in a parallel plate capacitor, right? So the capacitance of a parallel plate capacitor, the capacitance of a parallel plate capacitor depends on three things. Okay, so the first one is surface area. It depends on surface area. So the surface area of two conductive plates which make up the capacitor. The larger the area, the greater the capacitance. If the plates are larger, so that the charge can accumulate more, so that the capacitance will increase. Okay, the capacitance will increase, and also the distance. If the distance between the two plates, if the distance is smaller, then greater is the capacitance. Smaller the distance, greater the capacitance. Okay, so second parameter. And the third parameter, dielectric. Okay, dielectric material. The type of material which separates the two plates called the dielectric. Okay, the higher the permittivity of the dielectric, the greater is the will be the capacitance. So the capacitance of a parallel plate capacitor depends on three things, because this is the basic element. So the basic fundamentals, these fundamentals and this knowledge we can take it to further to higher devices like supercapacitors and batteries. That's why, so this information is crucial. Okay, that's why this information is crucial. Okay, so it depends on three things. One is surface area, so that means uh, The plates, the bigger the plates, the higher the capacitance distance. So distance between the plates very closer, smaller, close to each other, then the capacitance will be high. And the third one is dielectric. Okay, so this is about parallel plate capacitor. Then I will briefly introduce about supercapacitor, and further we will go in depth into the supercapacitors. So the fundamental thing is about supercapacitor is actually the supercapacitor is in between capacitor and battery. Okay, in between capacitor and battery. Okay, so if you see here, so in any energy storage device, so two parameters are very critical. Okay, two parameters are critical. So one is power density, another one is energy density. Okay, one is power density, another one is energy density. Okay, so you see this image. Yeah. So here supercapacitors in between, I said earlier, in between capacitor and supercapacitor. Electricity is a hugely versatile form of energy, but it suffers one big drawback. It's relatively difficult to store in a hurry. So that's what I said earlier, right? So we cannot instantly produce electricity and instantly utilize energy. For example, if you take thunders, right? Thunders will create huge energy, but we cannot capture that energy. So we cannot capture the energy. And also, even then, if we produce huge energy instantaneously, it is very hard to store that energy and further utilize that kind of humongous energy. Okay, and batteries can hold large amounts of power, but they take hours to charge up. So one of the drawback is batteries can hold the charge in larger amounts. It can produce large amount. It can produce larger amounts, but it takes to charge any battery. It will take so much time. Okay, that's why for example, whenever you charge a battery, it will take hours. If you charge an electric vehicles, it takes hours of time. That's why so batteries cannot instantaneously charge, but batteries can take more time to charge. Okay, then capacitors on the other hand, they can charge almost instantaneously because they store very less energy. Okay, but store only tiny amounts of power. Capacitors store a little energy but can it can be instantaneously charged. Okay, instantaneously charged. So supercapacitors are in between the characteristics of capacitors and batteries. So what is the drawback of capacitors? It cannot store more energy. What is the drawback of batteries? It cannot charge immediately. So the supercapacitor find a space in between capacitors and capacitors and batteries. Okay. So yeah, in our electric powered future, when we need to store and release large amounts of electricity very quickly, it's quite likely we will turn to supercapacitors. So, supercapacitors is in between capacitors and supercapacitors. So, what is the drawback in batteries? It takes so much time to charge, but supercapacitors can decrease that charging time. Okay, can decrease that charging time. What is the drawback in capacitors? They store more energy, but supercapacitors can increase that charge storage. But even then it has some problems, because supercapacitors cannot store more energy like batteries, right? And also, uh, yes. And also, so just like supercapacitors can instantaneously charge, but supercapacitors cannot instantaneously charge, but it can reduce the charging time when compared to batteries. Okay, when compared to batteries. Yeah, this is a type of supercapacitor. Supercapacitors have very high energy density than normal capacitors. Okay, supercapacitors have a very high energy density than normal capacitors. Supercapacitors use two layers of the dielectric material separated by a very thin insulator surface as the dielectric medium, whereas normal capacitors use only a single layer of dielectric material. Okay, right. That means, so supercapacitors use two layers of dielectric material separated by very thin insulator surface as the dielectric medium. But in normal capacitors, they use only single layer, because I'll explain in the coming slides. Okay. So and also normal capacitors are much cheaper than any supercapacitors in general. Okay. So capacitors are much cheaper, but it has its own disadvantages. Okay. It has its own disadvantages. So the capacitors, see, the supercapacitors store energy more than batteries. The charge movement is also very fast in this device. These are used for electric cars, elevators, locomotives, trains, and planes. Actually, this is wrong. So I'll correct. Right. So here you can see the differences between capacitor and supercapacitor. So I will give you some time. You can go through this table, so that, so before I am telling to you, you can get idea. So you can think of it. So just go through this table. So yeah, in capacitors, energy is stored in their electric field. Okay, energy stored as electric field. In supercapacitors, a supercapacitor is also known as ultra capacitor or double layer capacitor. The supercapacitor tends to differ from an ordinary capacitor due to its very high capacitance. So the main difference between capacitor and supercapacitor is in the form of storage, the form of the energy form, and also the capacity. Okay, and also the capacity. So energy here is stored in their electric field. Here the energy stored in as electrochemical energy. Okay, electrochemical energy here it is in the form of electric field. Coming to energy density, so energy density is comparatively low in capacitor and it is relatively higher in supercapacitors. Okay, relatively higher in supercapacitors. Dielectric material. Okay, dielectric material like ceramic, polymer films or aluminum oxide are used for the separation of the electrodes. Okay, for the separation of the electrodes. So dielectric medium we will introduce in between the parallel plates of the plates of a capacitor. Okay, so but here in supercapacitor, so we use activated carbon is used as a physical barrier between the electrodes, so that when an electrical charge is applied to the material, the double electric field is generated. This electric field acts like a dielectric. So usually we will introduce a separator thing like just like a dielectric. Okay, so the cost making a capacitor is cheaper, and supercapacitor obviously it is expensive. Battery even it is even more expensive. Okay, coming to the advantages. Coming to the advantages. Coming to the advantages, yeah, less battery drain. A car's battery does not deplete due to a capacitor. Okay, powerful stereos, amplifiers, and subwoofers working mechanism is based on capacitors. So these are the advantages of capacitors. Coming to the advantages of supercapacitors, supercapacitor and batteries are mostly used for energy storage purpose. Okay, mostly energy storage purpose, but capacitors are not used for that purpose. So that the capacitor's purpose is different. Wherever we need instant charge and discharge, and also wherever we need less energy, so there we can use capacitors. Okay, so high energy storage compared to conventional capacitor technologies, it possesses orders of magnitude higher energy density. It can store higher energy. So, and also less damaged equipment, it helps to avoid the excessive drawing of power. So the capacitors has more like life cycle time. We can use it for even thousands and thousands of cycles. But supercapacitors are not that much efficient. It is somewhat better than batteries, but not as capacitors. Okay, so supercapacitors is always the properties are always in between uh, capacitors and batteries. Okay, so this is what we have discussed earlier, right? So factors affecting capacitance. So actually, this slide must go here. So factors affecting capacitance C is equal to epsilon A by D. Okay. So A means area of the plates. Area must be higher. D means distance between the plates. D must be lower. So lower is better. Lower distance provides better capacitance. Epsilon is the permittivity of dielectric material. It is related to the dielectric material nature. Okay. So then I already told you why do we need supercapacitors? Why do we need? We already have capacitors, right? So why do we need supercapacitors? So to uh, to address the limitations of capacitors, that means lower energy density, right? Low energy density and energy density, we need supercapacitors. Okay, so capacitors, supercapacitors, and batteries. Okay, then fuel cells. So electrochemical, so it provides higher electrochemical, it is in the form of electrochemical energy, and supercapacitors provides higher power density, and supercapacitors provide fast charge and discharge nature. Okay, so these are the three things. Okay, so the energy stored in supercapacitors as electrochemical energy. Okay, electrochemical energy, and also it provides higher power density. Okay, higher power density, and also it can provide fast charge and discharge. Okay, fast charge and discharge. So if you see the images, you can see the capacitors, uh, capacitors, supercapacitors, and battery. So capacitors are in between capacitors and batteries. Okay, yeah, then this is very important to understand what is power density and what is energy density. So we discussed earlier that batteries have high energy density, and supercapacitors have high power density. Actually, what is power density? Power density is the amount of power in a given mass. Okay, power density is the amount of power in a given mass. Energy density is the amount of energy in a given mass. Okay, then supercapacitors has a higher power density. See, if you see the two mugs, if you take this cup, you can instantly fill the cup. Okay, you can fastly fill the cup, and also you can fastly deliver all the water from that cup, right? You can instantly pour all the water. So that if you take water, just like energy, if you take, so you can immediately fill the, you can fastly fill, and you can fastly pour, right? But battery, so see this bottle, so this bottle takes time to charge, and also it slowly deliver the energy. Okay, deliver the energy, but what is the major difference here? This cup store a little water, but this can can store more water. So that means supercapacitors store less energy but deliver fastly, right? Deliver fastly. Batteries can store more energy, and it takes more time to charge. It takes more time to charge. So this slide is very very important. You need to this picture should be stored in your mind, right? So supercapacitor belongs to power. Battery related to energy. Battery store more energy. Supercapacitor provide more power. Okay, so you should remember like that. Battery store more energy. Supercapacitor provide more power. Right, more power. See, some machines require more power. Some machines require more power, but some machines require more battery. For example, if you take a racing car, for example, racing car racing car requires more power, right? Racing car requires more power because it instantaneously, within seconds, it demands more energy. So super capacitor, like energy, it can deliver energy very fastly, right? But battery cannot deliver that much demanded energy within very short time. Okay, within very short time. So that's why supercapacitors provide power. Battery store energy. Battery store more energy. Okay, right. So yeah, supercapacitor has a higher power density. Batteries have a higher energy density. Okay, supercapacitors have high power density. Batteries higher energy density. Okay, supercapacitors can give off energy more quickly. Okay, supercapacitors can give energy very quickly, but batteries being able to store more energy. See, you need to understand. See, every technology or every method has its own pros and cons. Okay, more pros and cons. Supercapacitors can provide more power, but batteries can give more energy. Okay. One second. Yeah. So yeah, yeah, this is the major difference, major definition and difference between power density and energy density. Okay, power density and energy density. Okay, then sorry. Here you can see the difference between supercapacitors and batteries. So in previous slide, so we have seen supercapacitors provide more power density, right? So see, supercapacitors provide high power density. Okay, supercapacitors have higher power density. Okay, but so what about batteries power density? Batteries power density is low. Okay, batteries power density is low. Okay, so efficiency, coming to the energy storage, coming to the energy storage. So yeah, no, efficiency. So efficiency also less in batteries because we need to charge, discharge. So batteries doesn't have that much cyclability, but supercapacitors can provide for longer cycles, long. But if you compare this property with the capacitors, it is even very higher, even higher. But coming to power density, capacitors provide good amount, very little energy, right? Very little energy. So we cannot consider capacitor in this segment in power density, but in efficiency wise, capacitors are more efficient. Okay, capacitors are more efficient. Okay, power density wise, supercapacitors have higher power density, batteries not that much power density. Efficiency, supercapacitors are more efficient than batteries. Okay, than batteries. So coming to the this construction schematic picture of capacitors, ultra capacitors. Ultra capacitor is nothing but supercapacitor, okay, and battery. So in capacitors, we have two parallel plates. In between plates, we will introduce a dielectric. Okay, it provides very fast, high cycle life, low energy. Okay, it provides it can charge very fast, it can discharge very fast, and also high cycle life, thousands of cycles. You can charge, discharge, charge, discharge. But the drawback is low energy. Okay, the drawback is low energy. So, but where we use these capacitors, we have a lot of applications. We have a lot of applications. Okay, lot of applications. So, as a filter frequency control, we will use. So, in supercapacitors, so it is also very fast, but not just like a capacitor. But it has high cycle life, but not just like a capacitor. But it stores moderate energy. So here it is electrolyte in supercapacitors and in batteries. So between the anode and cathode, we should have electrolyte. Okay, electrolyte. So these two are electroactive materials that we can call it as cathode material and anode material. Okay, so here also we can this can one can be anode and one can be cathode. Okay, so then what about the properties of battery? So battery is slow. It slowly charge, slowly discharge, and low cycle life. So the cycle life is less. It is in the range of in the order of hundreds. Okay, in the range order of hundreds. It is in order of thousands. It is in order of 10,000s. Okay, 10,000s. So, but what is the advantage? It can store high energy. It can store high energy. So this is energy storage device. Okay, energy storage device. Okay, this is power delivery device. We can call it as a power delivery device, and we can call battery as a energy. The most first priority, the energy storage device is a battery, then supercapacitor, and then capacitor. So so out of three, which is the which can store more energy? Battery. Out of three, which can have more lifetime? Capacitor. So which has moderate lifetime and moderate energy storage? That is supercapacitor. Okay, supercapacitor is always in between capacitors and batteries, mostly in any property. Okay, any property. Yeah. So this is a schematic picture of supercapacitor. So this is electrolyte. Okay, electrolyte, charge, discharge, carbon based electrodes. Okay, carbon based electrodes. So among them, one is cathode and one is anode. Okay, we will see some important points related to supercapacitors. Okay, supercapacitors, also known as ultracapacitors or electrochemical capacitors. Why we are calling it as electrochemical capacitors? Why we are calling it as electrochemical capacitors? Because the energy stored in supercapacitors in the form of electrochemical energy. Okay, electrochemical energy. But in capacitors, the energy stored in the form of electric field. Okay, in the form of electric field. Right. So What are the basic principle of supercapacitors? Okay, basic principle of supercapacitors. So supercapacitors store energy through electrostatic charge accumulation at the electrode electrolyte interface. Okay, electrode electrolyte interface rather than through chemical reactions as in batteries. In batteries, so that is chemical reactions. Okay, in the form in the chemical so that is chemical reactions. Okay, chemical reactions. So lithium to lithium ions, tin to tin, Sn2 plus, Sn4 plus. So there is a change in chemical reactions. Okay, so that's why energy stored in battery, energy stored in the battery through chemical reactions. Okay, through chemical reactions. But in supercapacitors it is electrostatic charge accumulation where at electrode and electrolyte interface. Okay, so it consists mainly three things. One is electrodes, electrolyte, separator. Okay, electrode, electrolyte, separator. So typically made from carbon based materials with high surface area. So yeah, so from our previous lectures, we have seen one thing, that nanomaterials have high surface area. Why it has high surface area? Because it is at nanoscale. Okay, so the particle size is small. The average particle size is very small. So that's why it can offer more surface area. Okay, it can offer more surface area. Then what the electrolyte will do? So electrolyte provides ionic conductivity. So the ions can move from anode to cathode, cathode to anode, right? So that is the purpose of electrolyte. It provides ionic conductivity. Then separator. So what is the purpose of separator? Separator prevents short circuit while allowing ionic flow. So while allowing moving ions, so ions will pass through the separator, and it is acts it avoids short circuit. Okay, so energy storage occurs due to the formation of electric double layer. I will explain what is electric double layer. So at the electrode electrolyte interface. Okay, so the total capacitance is, the formula is same, so E is equal to epsilon A by T. So these three are the main parts in a supercapacitor: electrodes, electrolyte, separator. Okay, so this is electrochemical double layer, EDLC, electrochemical double layer capacitance, EDLC. An electric double layer is a structure appearing when a charged object is placed into a liquid. So this is the charged electrode. This is the charged electrode. Because of this, for example, it is negatively charged. Negative charge, negative charge, negative, 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 negative charge. So when these molecules comes close to the surface, so obviously it is the positive charges attract to this charged electrode. So then again, so here all negative charges. Okay, here all the negative charges. These negative charges, these negative charges attract here some of the, see again positive charge, positive charge. Okay, so here, so it is, see here plus, it is surrounded by negative, likewise. So another layer formed here. So this is one layer and this is another layer. So this is inner Helmholtz layer surface. This is outer Helmholtz surface. So two layers will form. That's why it is called electrochemical double layer capacitance. So the balancing counter charge for this charged surface will form on the liquid concentrating near the surface. Okay, so two layers will form here. Right. See this one. So types of supercapacitors. We have, how many types of supercapacitors do we have? We have three types of supercapacitors. One is EDLC, electrochemical double layer, and second one is pseudo capacitor, and third one is hybrid capacitor. Okay, hybrid supercapacitor. Okay, right. So this is the first one, electrochemical double layer capacitance. Okay, electrochemical double layer capacitance. See in this picture what you are observing. So this is one electrode, this is another electrode. Okay, so then it is a dielectric. Here it is a electrolyte. In electrolyte we have ions, positively charged ions and negatively charged ions. Okay, so then electrochemical double layer capacitors. Okay, so what are the properties of electrochemical double layer capacitors? So store energy through charge separation at the electrode electrolyte interface. Okay, so in electrochemical double layer capacitance, the energy stored through charge separation at the electrode electrolyte interface. You can see, so here positive charge and negative charge, here positive charge and negative charge. Okay, so this is electric double layer. Here the charge stored. Okay, so mostly we use carbon based material for electrodes. Okay, carbon based materials for electrodes, and as it is a supercapacitor, so it provides high power density but moderate energy density. Okay, but moderate energy density. Examples used in regenerative braking and power backup systems. Power backup systems means usually we will store, what is it called, power banks, uh, inverters. Yes, inverters. So in inverters we use, we need more storage, right? We need more storage. So in inverters, you can use this technology. Okay. So this is the main thing. Electrochemical double layer capacitors. It stores energy through charge separation at the electrode electrolyte interface. Mostly for the preparation of electrodes, whether it is anode or cathode, we will use mostly carbon based materials. And what is the main application of this one? So it provides high power density but moderate energy density. Okay, high power density and moderate energy density. Examples. So mostly the application is in power backup systems. Okay, power backup systems. So then pseudo capacitors. Okay, pseudo capacitors. So pseudo capacitors store energy through fast and reversible redox reactions occurring at the electrode surface. Occurring at the electrode surface. So materials such as transition metal oxides or conducting polymers are used. Okay, so in pseudocapacitors compared to EDLC, so energy stored through fast and reversible redox reactions. Okay, oxidation and reduction approaches. Okay, so it provides higher energy density than EDLCs, but slightly lower power density. Okay, so it stores more energy, and the thing is, pseudocapacitors is also in between. EDLC and hybrid supercapacitors. Okay, so pseudocapacitors is in between. So in case of EDLC, energy stored through charge separation at the electrode electrolyte interface. Here the charge stored through fast and reversible redox reactions. Okay, redox reactions. So then what is the third type? Hybrid supercapacitors, right? Hybrid supercapacitors. So it is the combination of both EDLC and supercapacitors. Typically, so one electrode is EDLC type, another electrode is pseudocapacitor type. Okay, so it offers the balance. Sorry, it offers the balance compromise between power and energy density. Example: lithium-ion capacitors. Okay, lithium-ion capacitors. It offers a balance between EDLC and pseudo-capacitors. Okay, right. See this slide. It is very important. Uh, we can find electrodes, electrolyte, separator, and current collectors. So these are the key components of any supercapacitor. These are the key components of any supercapacitor. Okay. Electrodes, the most critical component determining the capacitance and energy storage capacity. See, the electrodes are very important because the nanomaterials what we are prepared for the electrodes, that is very important. Okay, so based on the properties of the material with which we prepared electrodes, so that decides the capacitance. Okay, that decides the capacitance. That's why electrodes are most important component. Okay, most important component, the most critical component determining the capacitance and energy storage capacity. Electrodes should possess high surface area, good conductivity, and chemical stability. Okay, and chemical stability. Next, electrolyte. Electrolyte provides ionic conductivity by facilitating the movement of ions between electrodes. Okay, it provides ionic conductivity by facilitating the movement of ions between electrodes. The electrolyte should have high ionic conductivity, wide electrochemical stability window, and low toxicity. See, the second most important thing about the electrodes is, so usually we will prepare with nanomaterials, and this nanomaterial should have some properties, right? Should have some properties. What are the properties? It should have high surface area. Okay, it should have high surface area, and also it should have good conductivity. So good conductivity and also chemical stability. Without high surface area, we cannot store more energy. We cannot store more energy. Then without chemical stability, we cannot it cannot sustain for long cycles. So we will keep on charging, discharging, charging, discharging, right? So it cannot sustain for long cycles. Okay, so that's why we need a balanced electrode. We need a balanced material. It should have high surface area with good conductivity, with good chemical stability, right? So that's why electrodes are very important component in this supercapacitors. Okay, so then second one is electrolyte. So in electrolyte also it should provide good ionic conductivity. Okay, so previously we have seen, yeah, here the electrolyte should provide ionic conductivity. So why? Because So this electrolyte, the ions in supercapacitor will flow from one electrode to another electrode. So that's why it should have more ionic conductivity. Okay. So why? What are the purpose? To facilitate the movement of ions between electrodes. Okay. So if it is poor ionic conductor, then the ions cannot easily flow in the electrolyte. Okay. So that's why it should provide more good ionic conductivity, and also should have a high ionic conductivity, and it should have wide electrochemical stability window. And that means, so the potential window must be wide, so that it can we can operate in higher voltages. Okay. And also low toxicity. It should not be environmentally poisonous material or something like very toxic. Okay. Not poisonous, not toxic. It should not be toxic. Okay. So then the third one is separator. The third one is separator. A thin porous membrane placed between electrodes to prevent short circuit. So that's what the purpose of separator. So the separator, the separator's first assignment is, it should avoid short circuit. Okay. And also it should allow ions flow while blocking electrons movement. Okay. So electrons will these ions will flow from one side to another side, right, through the separator within so just like electrolyte, and the separator also in this electrolyte ions will flow. So this separator, so ions should have passed through the separator. That's why, so it should not block, the ions. And the fourth one is current collectors. So metal plates that connect the electrodes to the external circuit. Okay, to the external circuit. So should have excellent electrical conductivity and corrosion resistance. Okay. So the current collectors, just like copper or aluminum. So usually copper or aluminum we will use for current collectors. So they should provide excellent electrical conductivity. They should provide good conductivity and also corrosion resistance. Okay. So just remind these uh, points regarding key components of supercapacitors. So these are the fundamental and essential properties of the key components of supercapacitors. Okay. Right. The next one is materials for supercapacitor components. So yes, we have seen that electrodes, electrolyte, separator, right? But now our focus is on electrode materials. Okay. So what kind of electrode materials we can use to make supercapacitor, right? So okay. So yeah. So what kind of electrode materials we can use, what kind of electrode materials. So we will use carbon based materials and also metal oxides, conducting polymers, right? So we can use different electrodes, and each electrode has their own advantages in uh, advantages in preparation method or cost effect in cost purpose. So it has their own advantages and disadvantages. Okay. So activated carbon. So activated carbon has high surface area, low cost, and widely used. Okay. So it is very basic electrode material. Okay. It has high surface area, low cost, widely used. Graphene. Graphene is also a carbon-based, carbon family material, carbon-based material. So it has exceptional electrical conductivity. It has exceptional electrical conductivity and high mechanical strength. Okay, high mechanical strength, and carbon nanotubes. Okay, carbon nanotubes, high surface area, high surface area, excellent electrical properties. Coming to carbon nanotubes. Then carbon aerogels, lightweight and porous with good capacitance properties. With good capacitance properties. So these are some of the examples for carbon-based materials. So activated carbon, graphene, carbon nanotubes, and aerogels. So coming to metal oxides. So metal oxides used in pseudo capacitors for their fast redox reactions. Okay, for their fast redox reactions. Examples: ruthenium oxide, manganese oxide, nickel oxide, and cobalt oxide. Okay, for energy applications. Okay, so these are metal oxides. Will, for example, I have prepared tin oxide. Okay, SnO2 quantum dots for pseudo capacitor applications, and also conducting polymers exhibit high capacitance due to redox activity. High capacitance due to redox activity. So the conducting polymers also can be used as electrodes. Okay, so exhibit high capacitance due to redox activity. Polyaniline, polypyrrole, polypyrrole. Okay, pyrrole. So advantages: high capacitance, good conductivity, but there is some limitations that during regarding stability. Okay, so these are the electrode materials. Okay, so I will take you to some of my research articles that I have studied this supercapacitor for different electrode materials. Okay. So coming to the applications of supercapacitors, so we have seen that transportation, regenerative braking in electric vehicles, so consumer electronics, grid energy storage, and also medical devices. Okay, medical devices. So I will take you to some of my research articles we have discussed. So these are some of my research articles related to supercapacitor. So I'll show you one by one. So I have prepared some metal oxides, some metal sulfides. Hmm. See, for example, if you see this, it was published in 2024 recently. So I prepared a composite, nano composite. What is the composite here? MOS2 nanopetals and SNO2 quantum dots. And the application is supercapacitor performance. Okay, supercapacitor performance. So here I have prepared. Let's see. Yeah. So in first step, I have prepared MOS2 nanosheets. MOS2 nanosheets. This is the step one. Then I have prepared MOS2 nanosheets with tin chloride and thiourea with some approach. So I have prepared MOS2 nanosheets with SNO2 quantum dots. Okay. So I'll show you the images also. I think you are now aware of yeah. So this is a pure MOS2, right? Yeah. First two images are MOS2. First two images are MOS2. MOS2 nanopetals. Okay. So then this one, the images C and D. So these two are composites. MOS2 nanopetals decorated with SNO2 quantum dots. Okay. I think if you see the TM images, you can very clearly observe. See, these are the MOS2 nanopetals. You can see the clear layers, but in these images you can see, uh, um, yeah, see the nano layers like petals with MOS2 quantum dots. Okay, these are all quantum dots. So these agglomerated clouds. So these are all SNO2 quantum dots. Here you can see clearly. So this is MOS2 layers. This very dark layer, dark region. So that is MOS2 layers, and these are all SNO2 quantum dots. Okay, SNO2 quantum dots. So yes, this is called cyclic voltammetry. So where you can perform electrochemical study. Okay, electrochemical study. So it gives, yeah, this is charge discharge, charge discharge. Here you can see. So, so this is the charge. This is the charge condition, and this is the discharge condition. Okay, discharge condition. So it is, yeah, this is the time, charging time, and this is discharging time. So this is the potential. Okay, so this is how we test the electrochemical performance. Okay, electrochemical performance. So this is one electrode. I told you this is one type of electrode. Okay, yeah, these are the some images. Okay, then we will see another material, that is tin niobium oxide. Okay, tin niobium oxide. You can see the 3D morphology here. Okay, see this porous structure. Okay, particles agglomerated, looks like a 3D bulk material. Okay, so here also you can see. So this is the charging and discharge condition. Okay, charge condition, discharge condition. Okay, for every material. So we have prepared three materials. Here you can see the comparison. Yes, the red one is SNO2, and the black one is niobium oxide, and the blue one is tin niobium oxide. It is a nano composite. So these two are individual ones. So this is the combined one. So combined one provides obviously higher capacitance. Okay, higher capacitance. You can see here also. So the curve with more space. Okay, the more space, that means more capacitance. Okay, so this is about another uh, metal oxide electrode. So I wish to show you the electrode, different electrode materials, right? Different electrode. Here we have seen, right? Here we have seen, yeah, different materials, different electrode materials. For this purpose, so I'm showing you all these things. Okay. Okay, so this is about another material, and we will see another one. So yeah, this is SNO2 quantum dots. Okay, SNO2 quantum dots, and this is about, yes. So see this one. Yeah, this is CV, cyclic voltammetry, and this is the charging discharging at different current densities, different current, 1 ampere per gram, 2 ampere per gram, 3 4 ampere per gram, like this. So at different ampere per gram, so charge discharge. So this is the cycle stability. You can see here up to 5,000 cycles. We have tested up to 5,000 cycles, right? Up to 5,000 cycles. See this, 1,000, 2,000, 3,000, up to 5,000 cycles. This is the charge discharge condition. Okay, so this is another. If you see this image, yeah, yes, right. Carbon nanoparticles and SNO2 quantum dots. See, these are carbon nanoparticles. Okay, carbon nanoparticles. This is SNO2 quantum dots. In some usually look like agglomerated particles. Here you can see the carbon particles, and these black, these are all uh, dots, quantum dots. Okay, see here also you can see. So these are all carbon nanoparticles, and this is quantum dots. Okay, carbon nanoparticles, carbon nanoparticle, carbon. So and this is SNO2, 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 SNO2. So these are all SNO2 quantum dots. Okay. So next we will see another material. Yeah, this is amexin. Okay, amexin. We will see amexin. So yeah, this is amexin nano sheets. It's a 2D structured material. Okay, 2D structured material. So here also we can see the supercapacitor performance. Yeah, supercapacitor performance. So we have prepared in three ways. Okay, so charge discharge conditions. Yeah, charge discharge, charge discharge. This is cyclic voltammetry. Okay, cyclic voltammetry. So this is one type of electrode. Okay, so we have different electrode materials, different electrode materials. Okay, and this is another amexin ink. Okay, amexin ink. You can see, yeah, you can see the beautiful pictures. Okay, 2D layers. two-dimensional layers. See 2D lines. Yeah, this is microspheres. I have prepared this with hydrothermal approach. See the microspheres and how about supercapacitor performance? Yeah, nice, right? So this is cyclic voltmeter graph, and this is charge discharge. Okay, charge discharge at different current densities. Okay, so this is the sun picture. See the microspheres with nice porosity. Okay, with nice porosity. This is the cycle stability, and yeah, this is EAS diagram, EAS analysis. Okay, and the last one. So niobium tin molybdenum sulfide. I don't have access to this. So this is the device structure. So these are some of my research articles related to electrode materials. Okay, related to electrode materials. Okay, so this is about supercapacitors, energy storage devices. Okay, so these are some of the applications, supercapacitor applications. So public transportation. Okay, we will use in public transportation also. Hybrid buses, hybrid buses and other vehicles can benefit from supercapacitors. Wide operating temperature in China. I think in Europe also. So we have some hybrid buses already used supercapacitors to boost acceleration, and supercapacitors help trans travel from one stop to the next, recharging at the stations. Okay, so already it is under usage. Okay, so we are using, even we are not in India also, we are using many electric vehicles, right? So for electric vehicles, we need a combination of supercapacitors and battery, because batteries cannot give uh, fast energy. It cannot supply power, right? So for that purpose, we need the combination of supercapacitors and batteries, hybrid vehicles. So the supercapacitors can deliver wherever it requires high acceleration, and batteries can provide storage of more energy. Okay, so these are the applications of supercapacitors. Okay, so this is about today's session. So just I want to take you all the slides. So yeah, this is our starting point, energy storage devices. Okay, so we have discussed different types of energies, different types of energy storages. Okay, I will show you. Yeah, these are the different types of energies: solar to wind to hydro, tidal wave, right? These are all different types of energies, thermal energy. Hmm? So but our prime focus is electrochemical energy, right? Electrochemical energy. So these are all different types of energies. So our prime focus is, so, and also these are some of the energy conversion methods, right? Energy conversion methods. So wind energy, solar energy are green energies, and these green energies that we produce can be stored as chemical energy in batteries, right? In batteries, and so that we can use it wherever we want, whenever we want. Okay, so that is the advantage of this electrochemical energy. And electrical energy is the most convenient energy to use very simply, right? Then capacitors. So parallel plate capacitor is the basic element, and it depends on three parameters: surface area, distance, and dielectric material. So this is the energy density and power density chart. So lithium ion batteries provides high energy density. Okay, lithium ion batteries provides, see the on y-axis energy density. Lithium ions are the highest energy density. Okay, then power density. So power density wise, supercapacitors provide a balanced power density, higher power density, and also balanced energy density also. Okay, so the capacitors, but capacitors provide high power density but low energy density. Okay, so fuel cell is not our topic right now. So these are the comparisons. So why do we need supercapacitors? Because to address the limitations of batteries and capacitors, right? See this, see the picture. You can understand power density and energy density. Supercapacitors providing high power density, batteries providing high energy density. Okay, high energy density, right? See this one. This picture gives you the information about power density and efficiency. Power density and efficiency. It gives the comparison between capacitors, supercapacitors, and batteries. Capacitors provide very fast charging discharging, high cycle life, low energy. Supercapacitors, very fast, high cycle life, and moderate energy, right? Moderate energy. Batteries provide slow charging discharging, low cycle life when compared to supercapacitors and batteries. But what is the prime potential of battery? So that is, it can store high energy. Okay, it can store high energy. So this is about the introduction to supercapacitors, right? Basic principle of supercapacitors, right? So main three components: electrodes, electrolyte, separator. This is about electrochemical double layer. This is about electrochemical double layer capacitors. Electrochemical double layer capacitors. It stores energy at electrode electrolyte interface. It provides high power density. Mostly used at in, just like inverters. Okay, power backup systems. We'll use it like a power backup system. And pseudo capacitors. Okay, pseudo capacitors. It can store higher energy density than EDLCs. It can store higher energy density than EDLC. Hybrid capacitors is the combination of EDLC and pseudo capacitors, because mostly in EDLCs we will use carbon based electrode. In pseudo capacitors we will use metal oxide based electrode. In hybrid capacitors we will use the combination. One electrode made up of carbon based material, and the another electrode can be made up of metal oxide, so that it can be the combination between both, so that it can balance both power and energy. Okay, so power part can be taken care by carbon based material, right? So and then energy storage part can be taken care by this metal oxide thing. So that's why it is a balanced approach between power and density. Examples: lithium ion capacitors. Okay, so these are the key components of supercapacitors, right? Electrodes, electrolyte. So these are the properties that the four components must have. Okay, electrode should provide high surface area, good conductivity, and chemical stability, right? Electrolyte should provide higher ionic conductivity. Separator should avoid the shortage. Okay, electrical short circuit. And separator should not block the ions. Okay, and the collectors should provide higher electrical conductivity, and there should be corrosion resistance. Okay, so these are the different types of electrode materials. So we can use any of the material, depends on our requirement. So these are the applications of supercapacitors. Okay, yeah. Thank you for watching this video. I hope you like it. I hope you learn many fundamental things related to energy storage devices, particularly supercapacitors. And we have also covered the basics related to energy production and energy conversion and energy storage. So we mostly focused on energy storage. Okay. So thank you for watching this video. If you like this information, please like the video. And if you have any queries, please comment below. I will answer your queries. Okay. Please share with your network. Please share with your friends, and uh, thank you. Thank you so much. See you in next video.